shelves and moved some heavy furniture. The heaviest shaking occurred within a 21.66 square mile region, receiving maximum shaking midway through the quake, which was approximately equivalent to an MMI of 6.5 or ground acceleration more than 20% the force of gravity. Thankfully, no damage was subsequently reported, likely owing to the fact that only 50 people lived in the aforementioned area which experienced the heaviest shaking. Then, across the next 19 hours, a total of 324 earthquakes struck the same location in fairly rapid succession, including 3 magnitude 4 range earthquakes, the largest of which was a magnitude 4.6. The rate of aftershocks largely followed the typical 1/x frequency, with aftershocks x representing a unit of time that starts at a value of 1, as you can see in this chart. However, on the U.S. Geological Survey webpage for this event, it states that during the next week, there is a 17% chance that a magnitude 5 aftershock will follow, a 2% chance of a magnitude 6 quake, and a 0.2% chance of a magnitude 7 quake being triggered. The latter two of these are quite unlikely and only possible on more distant and longer active faults. The 5.2 main shock was also one of the only 6% of earthquakes in California to follow a foreshock quake, a magnitude 4.2 on June 24. What had just occurred were an earthquake sequence and its associated aftershocks that occurred due to the movement of a largely unknown but medium-sized fault line. I am not referring to the San Andreas Fault, which is located 18 miles to the south, but an unnamed fault line which trends southwest to northeast and was previously mapped as being around 4,650 feet long. While the San Andreas fault line almost always fault type produces earthquakes which a near pure strike-slip motion, this fault line produced oblique motion, more specifically, that of an oblique left lateral reverse fault. It is quite likely that the entire fault line ruptured in the subsurface, whose magnitude suggests a rupture length of 7,650 feet, meaning the fault line is likely longer than previously thought. This fault is one of 37 adjacent small fault lines which have been historically active in the southern portion of California's Central Valley, seemingly accommodating motion generated by larger adjacent faults and a slight compression in the region. These faults have produced a total of 10 magnitude 4 quakes and 1 magnitude 5 quake unrelated to the latest sequence. Earthquake intensity comparison. Yet, this earthquake resulted in a peculiar observation, as it seemingly generated more intense ground shaking than would be expected given its only moderate magnitude, with it mostly matching what would be expected with a larger magnitude 5.8 earthquake. So, why did Tuesday's earthquake cause more intense shaking than these 3 exact same magnitude 5.2 earthquakes that struck California in prior years? The answer is the surface rock unit the relevant earthquake the epicenter was located beneath. While the 3 other earthquakes of the same magnitude struck hard host rock, whether this be sedimentary, metamorphic, or igneous rock, this week's earthquake instead struck beneath an alluvial plain. In other words, the earthquake struck an area filled with numerous small sand-sized particles, while the other 3 quakes occurred in areas with largely solid rock. These small grains are not only much more porous, meaning that a cubic meter of it has less density, but it also is able to hold more water between these spaces than the harder rock counterparts. When seismic waves pass through liquid versus a solid, they slow down, but since the energy remains the same, they increase in amplitude. The same thing occurs in rock units that are less dense, such as an alluvial plain, resulting in more intense shaking from the same magnitude earthquake. As a final note, I would like to thank my new Patreon